Welcome back. So tomorrow is a workshop day, so this is the last talk of the colloquium series on robust and beneficial artificial intelligence. Our speaker is Andrew Critch, a research fellow here at Machine Intelligence Research Institute. Andrew got his PhD in mathematics from UC Berkeley and co-founded CFAR and worked at Jane Street Capital for a while. And he's here today to talk about ways to have coordination between bounded algorithms that can read each other's source code. So let's join me in welcoming Andrew.
Thanks. Okay, so let me call this. This is in the frame. We're here. Cool. So I'll call this talk "Robust Cooperation of Bounded Agents via a bounded generalization, a parametric bounded generalization of Loeb's theorem." And let me give an outline, which I will immediately relabel to menu, because we're a very small group, so you can just kind of steer me through the outline in a choose-your-own-adventure collaborative game that you have to play with each other, so be sure to cooperate. So I'll start with what I'm going to call open source prisoner's lemma. The OS stands for open source. It also stands for one shot. So open source one shot prisoner's lemma. Prisoner's dilemma. Next will be attempts at robust cooperation. In that scenario. Next will be, I'll probably talk about the bounded generalization, parametric bounded Loeb's theorem, or PBLOB. And then, to the extent that it wasn't quite covered in this section, which is optimized for pedagogy, I might want to say some more about the history of these results, where they came from, and then possibly also future directions for this stuff. Great. And so knowing that these things are all on the menu, you can like try and get me to jump forward or backward or whatever you want. Cool. So just so I can find out who I'm talking to, I know like about half of you guys, I guess, and I've met more than half. So first of all, who has read a paper by Patrick on robust cooperation? Okay, so about half the audience. So this will be for mostly.
Your paper.
Oh, my paper. Oh, that's worse. Okay, so you read so who's read Patrick's paper on robust cooperation or my paper? Oh no. All right. So you guys should be giving me the talk. And all right. So I know I'll skip through this pretty quickly then. Probably skip through this pretty quickly. Maybe I might spend more time talking about this or like interpretations of the results, or the talk could just be less than an hour. We could just like be done quickly. Okay. So I'll just so hands up for the compliment, the people who have neither read my paper nor the robust cooperation paper. Okay. So I'm talking to you guys. So open source prisoner's lemma. I'll just illustrate it by some example agents. So an agent takes its opponent's source code and then returns cooperate or defect. That's like the format of the game. The agent also has access to its own source code, which you can do by quieting if you like functional programming, or you can just like have it as a primitive in your language that you can read your own source code. So secretly, it's also got access to its own source code. But I won't always denote that. So example. We'll have an agent called cooperate bot, which I'll just like write CB because it's short. We're going to say define cooperate bot of opponent equals return cooperate. So it's very simple. It just like ignores who its opponent is. It cooperates with the opponent no matter who that is. We can define another agent, which I'm going to call isMeBot. And as far as I can tell, this agent was first written down by Tenenholtz in Games and Economic Behavior 2004. So I'll just like put a little citation here.
Actually, there's someone who came out with that in the 80s.
Oh, really?
Yeah.
All right, well, I'm going to cite him for it. Tenenholtz, Games and Economic Behavior 2004. And isMeBot just says if the opponent equals me, then return cooperate, else return defect.
Right. Okay. Anyway, Howard and McAfee in like the 80s, but I also put up there, but whatever.
Okay, I'm not going to cite them because I'm not sure I want to.
Okay.
Yeah.
When did Hofstadter write about supervision analysis?
He did not come up with it.
Yeah, so there are people thinking about things like this.
No, but still.
The 70s.
Yeah. Like, I'm interested in this because this is the point in which, this is the paper where the notion of program equilibrium was defined, where you can think about a Nash equilibrium where you and I are about to submit programs to play a game against each other, and there's a Nash equilibrium between us as the programmers, but not really between the programs playing the game. Anyway, okay. Next. So, if you wouldn't mind, let me follow my own narrative track here, because I think I'm going to explain this a little bit different from the way Patrick normally does. So, the way I think about this is that this agent is very fragile, because there's like only, you know, it's interesting, you know, it can achieve cooperation with itself in a one-shot game, which is cool. Usually you don't see cooperation in Prisoner's Dilemma unless there's like iteration, where there's some, like a lot of examples you've seen tournaments, right, where agents participate in Prisoner's Dilemmas with each other over and over, and when you have a reputation to keep up with your opponent, then you like cooperate more to try and get them to cooperate with you later. But in a one-shot game, there's like no incentive to cooperate if there's, unless maybe something's different, like your source code is visible. And in this case, you know, you end up cooperating with yourself if you're isMeBot. But what if isMeBot is written in Java and there's another isMeBot written in C++? They don't cooperate. So it's kind of fragile in that way. Even though like they're the same idea, they don't cooperate. So we can say this is fragile because it uses kind of like a fragile cooperative criterion. So Patrick and others were looking at a more robust criterion, which motivated this guy. And I'm going to skip over I'm just going to skip right to the bounded version that I have in my paper. So this is going to be fairbot. And you can imagine, well, okay. It's a question of what's actually going to happen here. Is this going to work or not? But like, let's just say what happens when you bound this thing. So fairbot looks at its opponent, and it's going to search for a mathematical proof. So you fix some proof system, let's say piano arithmetic, of length less than or equal to k characters. So imagine it's just a text file, and we're counting the number of characters in the proof, that the opponent cooperates with Fairbot. And like this is a mathematical statement. And searching for a proof, you can search for a proof lots of different ways. You can search for a proof by running the program, but you don't have to prove stuff about programs by running them. So like if I say while n is n is 0, while n less than 1,000, increase n by 3, and ask you what that program outputs, you can like think about it for a second and realize it's going to output the first multiple of 3 after 1,000, which is 1,002. And you didn't have to think of the number 501 while you reached that conclusion. You did not have to simulate the program. You only needed to reason about it. You could run it, that's another way, but I'm going to allow any kind of proof that the program outputs a certain thing as part of the reasoning process here. Cool? Okay. So this is you search for the thing you search for a proof of, and then if found, where found is like a Boolean, return cooperate, else return defect. So I can already tell from the audience that this is not going to be the version of this talk that, where's Alex, that will go on the internet, because too many of you already know how this turns out. Or how it's eventually going to turn out. But the question is, how does this bound affect the proof search? So just for like the 3 people who have not read, I guess probably I've already talked to Stuart about it. So there's only 2 people. So for you haven't seen this? Okay, yeah. So what happens here? Everybody just like take 30 seconds, think for yourself what happens when Fairbot encounters Fairbot. So we can do a warm-up question. Warm up. What is Fairbot of cooperate bot? And everybody wave your hand at me when you have an opinion about what this is. Just like wait, you don't have to raise it, just go like, I have an opinion. All right, what's our opinion? Not from Patrick. Patrick knows more about this than I do, so I want to engage you guys more. Yeah. Not quite.
No, of course not. Yeah, defect.
Not quite.
Depends on k.
Depends on k. So if k is small, there's not going to be any proof. If I say, find me a proof using 1 character that cooperate bot cooperates, then it will find no such proof. Does that make sense? The proof's too short, right? So equals C, for k sufficiently large, maybe k needs to be like 100 or something. I don't know how many characters you actually need to write a proof that that thing cooperates. But it's pretty short. Okay, so that was our warm-up to make sure we're all thinking about how the code really runs and not just being intuitive about it. Question? Yeah.
Cooperate bot. Oh yeah, sorry. Yeah, I confused it with SB bot. Yeah, sorry.
Yeah. So fair. Yeah. So I'm just going to skip ismebot for now. And next question is, what happens when Fairbot sub k in this form, this version of Fairbot k, runs against itself? And maybe just think about that for 30 seconds and give me a wave when you have an opinion. Okay, so here's what I want to do. This means cooperate. This means defect. Okay? So I want everybody to make your best guess whether this is cooperate or defect.
For what k?
Let's say, yeah, good question. So let's say k is big. So obviously we already saw if k is small, it doesn't cooperate. So let's just say for k large, let's just say for k is 10 to the 100. Okay. Everybody ready? Prepare your hand, cooperate or defect, go. All right, so we have some bimodal answers. Some people are doing this. Some people are doing this. Okay, Cool. So let me hear from the people who are saying defect. Do you see the defects? Okay. Why?
I don't know, it just seems like you need to think farther than in case steps if you want to think about someone who reasons case steps. I don't know. That's my intuition.
It's other people who say defect are having similar intuitions?
Similar that if that you can't contain something at that length if you only have the same length.
Somehow.
This is the thing you didn't say was that K is like encoded in binary.
Yeah, it's a computer. Yeah.
That's not the reason I thought.
Yeah. And I saw at least Soon had like a C or D thing going on, like this.
Yes, it was underspecified.
Underspecified. Interesting. Okay, so which part of the code is like not specified enough?
Well, you can't get a computer to run that thing. Depends on how it's searched. But
okay, why don't I do this?
it seems stable.
Now can a computer run it? I'm not going to do.
No, that was not the problem.
Trust me.
It is. I mean, there are more than one way of implementing that.
Sure. Yeah. Right. Okay. So you would like to pin down how you're searching for the proof?
Both. So because of that, you could imagine that both things were possible, and it seems that both C and D should be stable.
So here's an interesting question, right? So what's the argument for C and D being both plausible? Yeah.
If you didn't know which was which, then you couldn't recover that information. By looking at the specification.
Let me try and make an argument. Yep.
Maybe the solution space is underspecified. I'm not saying, this is feasible for any finite K. This is maybe an answer that you can only...
So first of all, great. I'm glad these thoughts are all coming up because I want to make sure that we're thinking concretely enough about this to have these questions. Otherwise, the result will seem like kind of weird or like it'll be vague and it won't be clear what it means. So, first of all, let us note that this program halts. I can bound its runtime. It's going to run in something like 2 to the k steps, however long it takes to search for this many proofs, and then it will give, if it finishes the search and found no proof, it will give up in defect. So this has a bounded runtime.
Okay, but you didn't specify that before.
No, I don't have to. It's right here in the code.
I see.
Right? So corollary of the code, consequence, is that the runtime can be bounded. Another thing that we should need to specify is we maybe need to specify how we're searching for the proof. Right? Is it just like a heuristic search? So let's just say we're going to alphabetically search through, for the simplicity of you guys analyzing it and me analyzing it, let's just assume we're going to search alphabetically through all strings and then check, is this string a proof that my opponent cooperates? One sec. So search alphabetically. Through strings for a proof. So soon, does this seem like it has specified? I can also say a proof in piano arithmetic. And I can say in piano arithmetic using standard Gödel encoding with binary abbreviations for numbers to save space. Using binary for numbers. One reason it's important to use binary for numbers is that this symbol will get really big if you use the successor operation to encode numerals. So you definitely want to use binary. Yep.
I don't know if you want this comment, but it doesn't matter how we search as long as we search it exhaustively.
Somebody thinks it doesn't matter how we search. Somebody else might think it does. Does it matter? For example, maybe it seems like cooperate. So there's at least a few people here who think that cooperate and defect are both consistent answers, and so maybe whether you get C or D depends on the order that you search. Any more thoughts in the arguments?
It does not matter the order that we search because
you think it doesn't matter?
Searching for one thing. If we were searching for proof of cooperate and for defects, we might find one first. But it's just, is there proof of cooperate?
Well, but hang on. The proof is going to be about the search method, right? So maybe, right?
I guess you can prove it.
So you're proving a different thing. You're proving it, whatever the search method is, the proof is going to be a different proof.
I guess you could prove reasonably quickly that no matter how you search through it, you're going to find the same results.
Really? Can you? How do you?
Okay. I don't know.
Use some search method that's provably equivalent to.
And I think that statement is wrong.
I don't know how to do that.
I mean, it's provably. Oh, okay.
Yeah.
Because think of it. The point is, if I fixed a single statement, right? If I fix this, the interesting thing is that like Fairbot takes as a parameter this like proof search method, right? So if I just fix a single proof statement like Riemann hypothesis, if I put here, if I don't have Fairbot here, if I just say search for a proof of Riemann hypothesis, then yeah, I agree that the search method doesn't matter. Because all that matters is whether exists a proof of Riemann hypothesis in these characters or not, right? Problem is, the statement you're proving has as part of it the proof search method. So if I change the proof, if I change the proof search method, I don't just like find another method for searching for the same result. I've like changed the result I'm also searching for.
The two search methods should give the same result on any particular
If you can prove
result.
that.
Then
Yeah.
Okay.
Yeah, if you could prove that, that'd be interesting.
Worse, it depends twice.
Anyway,
Because it's even worse because your opponent is also a Fairbot, so it depends twice.
It depends twice on the proof search method. Yep, that's right. Yep. So those are some subtleties.
Take down your hypothesis.
Take down. I was thinking about doing that next semester actually. Thanks, Patrick.
You're welcome. I set you up.
Yeah, I was an assist. All right. So those are the things. Now, there's for people who are the people who are feeling like C and D are like both consistent. So think about this. Only like this is a program. It's deterministic. Once I've fixed my proof search method, and I've like it's got to output C or D. It's got a bounded runtime. It can't run forever. So
the proof search has to be deterministic as well. Then.
Yeah, that's right. So this is I'm not drawing any random numbers during my program. This is like a deterministic computer program with no cosmic rays hitting it. Yep. Cool. All right. So now that we've had a little time to deliberate, repoll. So hands up for indicate, cooperate, defect, or this would be like don't know. Okay, go. Don't know. Got some C's. Got some don't knows. Got a D. Cool. All right. Why do you think D?
Same people, same reason that people are saying D.
Basically, it's not going to have enough time to like reason about a thing that's reasoning about this much length. Cool. Yeah. So this is, I think, we've like now thought like I feel like I've tried to presenting what's going to be next in a few different ways, and I find that if I don't give people enough time to think about it, it sort of fails to be as counterintuitive as it should be. So the answer is cooperate. And for the people who said cooperate, is it because you know Loeb's theorem? Yeah. Right. Okay. So answer is cooperate.
Also because, like, why would you have used this example otherwise?
Yeah. Well, so empirically, sometimes people start talks with things that don't cooperate as a way of, like, illustrating why it's interesting. So, yep. So, and I did say, I don't know, I said attempt. Anyways, you guys all know the results, so it doesn't work. But I just wanted you to think about it long enough to feel like, actually, it's not so obvious. Great. So it's cooperate, and just to review the intuition, which was, I guess Vladimir Slepnev was the first person to think about using Loeb's theorem to like get things to cooperate. Which is, so Loeb's theorem is that if piano arithmetic can prove that if a natural number encoding a proof of P exists, then P is true. then P-N arithmetic can prove P directly. So hands up for people who would have written Loeb's theorem on the board had I just asked them to do it. It's going to be like a half. Yeah, great. Okay, so this means this is like an arithmetic statement that means a proof exists of P. And this also means a proof exists, but it's like a different language using to state that fact. So this is like exists a natural number encoding a proof of P. Cool. So that's Loeb, and basically it almost applies here when you let P equals, if you ignore the K for a second and blur your eyes and pretend like things aren't bounded, or look for some kind of fixed point in some logical universe, then you feel like you want to write down, if there's a proof of cooperation, Faribault will find it and therefore cooperate. Does this part make sense? P is cooperation. So this feels like if there's proof of cooperation, they'll find it. And moreover, I can write down an argument for that. P-N arithmetic can understand that argument. Therefore, P-N arithmetic can prove that cooperation happens. Therefore, cooperation happens because we believe P-N arithmetic. We think this thing believes P-N arithmetic, and that's its criterion of cooperation either way. So that's interesting, and actually Patrick and others developed a framework for writing down formulas like this, like this for cooperation of various agents, and kind of thinking about what they would do to each other in a universe with like unbounded computational resources where things can sort of search instantaneously through proofs and also search instantaneously for proofs about those things, etc. Is that fair?
Yeah, you can just say oracles though.
Yeah. But the problem is that sort of none of those agents are bounded, and it's like, okay, Loeb's theorem is kind of weird, right? So who's thought about why Loeb's theorem is weird? Okay, fewer. Okay, so, the Riemann hypothesis, if this is Riemann hypothesis, then it's very tempting to believe this statement, right? It's like, well, I don't know if the Riemann hypothesis is true or not. But if I prove it, it's true, right? So you're like, yeah, if I prove the Riemann hypothesis is true, well, the problem is if you ever wrote down a proof of that claim in P-N arithmetic, then you would shortly thereafter write down a proof of the Riemann hypothesis, which is bad news if the Riemann hypothesis is false. So until you know the Riemann hypothesis is true, you don't want to believe that you're trustworthy about it in the positive direction. So that's the weirdness of Loeb. Some people call this the Loebstacle. It's like an obstacle to self-trust. And it's often viewed as a negative result. And then sort of Slepnev noticed that you could also use it to get like a kind of positive thing to happen, like cooperation. And a lot of people, when they see Loeb, they're like, well, that's weird, and it's got infinity in it, namely this existential quantifier that searches instantaneously through all natural numbers and determines whether a proof for something exists, right? So maybe the weirdness of Loeb's theorem is coming from infinity, right? Maybe if we write bounded programs that do bounded reasoning, the weird stuff will go away. Anyway, the answer is no. The weird stuff does not go away. And here is this, so yeah, maybe only one person actually read my paper. So apologies for the person who already knows this result. But parametric bounded Loeb is that if P-N arithmetic can prove that for all k, so we're going to fix some statement that takes a parameter k, like Faribault cooperates with Faribault. And we're also going to fix some function f of k that grows faster than some function of log of k. It's going to depend on the proof system. I think log k cubed. I'm like fairly confident log k cubed is enough. I'm also fairly confident that log k is enough. But if we go log k to the 5, I'm like, hell yeah. Okay? So some function.
And the exponent depends on things like whether you're using binary encoding for numbers.
Yeah, so we're definitely, actually, if you're, no, the log depends on whether you're using binary encoding for numbers. If you don't use binary encodings, you have to replace log by like whatever your encoding is. The exponent comes from how efficiently you can encode proofs about yourself, or like proofs about proofs. So if you have a proof of length n, how much space does it take to prove that that proof of length n is a proof of length n? And I'm pretty sure MetaMath can do this in linear space, like the amount of time it takes to verify a proof. Yo.
Is this for reasonable proof systems?
Yeah.
Can I make the proof system?
Oh, you can make it super unread. Yeah. Well, you could make it piano arithmetic using the successor operation for encoding numerals, and then that's already pretty bad. And you could make it. You could probably make it worse if you wanted.
So the log k to the 5th is reliant on it being reasonable.
Yeah. This is like this for the 5. The log and the 5 are like 4 reasonable things. Like things. If you ever wrote a program to do proofs, there are certain efficiencies you take advantage of. For example, if you want to check whether modus ponens is being applied, it's nice to like have a pointer to like where the arrow is in the middle of the modus ponens to save space in the search for that. So an efficient proof system would like start an application of modus ponens with like a little number that says like where the arrow is in the modus ponens so they can check it efficiently. So like little things like that. If you do things like that, then you can probably get it down to just that. But some number n goes in there depending on how efficient that's going to be. And so I'm just going to wrap all that up into like there's going to be like some polynomial function of log. Okay, are we cool with that? It depends on the proof system. All right, but whatever it is, if f is bigger than that, and if piano arithmetic can prove that for all k, a moderately long proof of p of k, so f is our like measure of like moderately long proof, is sufficient to deduce p of k. If you can show that long proofs, if you can show that you trust yourself about proofs that are fairly long, but not crazy, you don't need to trust yourself about crazy long proofs, just like moderately long ones, then piano arithmetic can prove that for all k past some threshold, p of k starts to be true. So it's just exactly what you want for pair bots to eventually cooperate for large k. This is kind of nice. It's not coincidence. I was just like aiming for anything that would make pair bots cooperate, so that's why this is the result I got. Questions?
Sorry, what's the symbol in front of the log at the top?
Yeah, this is my like function that like takes into account how efficient it is to encode proofs to have proofs about proofs, and it depends on the logical system. So it's going to depend a lot on, this thing here. Yeah. Stuart.
Oh, for the Fairbach proof, do you need that f?
Well, you do need this whole thing to be less than k. And so I'm pretty sure like log to the 5 is less than k, so it works out. So application.
Because there's also the Fairbots have to register the k, because that's part of their definition, and that varies.
Right.
Okay.
Every time you increase k, you also slightly increase the complexity of the thing that you're proving by making it like slightly longer. Yeah. Other questions? Yeah.
Why is this true?
Because there's a proof. Yeah.
Oh.
Fair? Yeah. Yeah. Good.
The really weird part is that it seems that the bots will cooperate by just proving more or less by proving this bounded lobe theory.
Yeah.
And concluding
Yeah, that's what happens. So,
Yeah.
So, Daniel, my intuition for why things like this are true is that they can be readily turned into statements about Gödel's second incompleteness theorem. So this is, in fact, equivalent to a statement that if a certain extension of Peano arithmetic contained a short proof of its own consistency, then it would be inconsistent.
Okay. Sure.
Yeah, that's probably true. At the very least, a result of that form, I'm pretty sure that a result of that form could be used to prove this.
Okay.
And this might be a little bit too weak to get what you said, I'm not sure. But the reason I'm calling this parametric bounded lobe is because I'm saving the name bounded lobe for maybe someone proves something slightly more basic than this. Yeah. So you let f of k be whatever, like I think this is, you just want it to be epsilon inverse of k, I think. Epsilon inverse circle k. So if epsilon is like cubing, then you can just take cube root of k. Or f of, yeah, okay, anyway, I might fix that as we go. And then let p of k be this thing. So what do we have? What we have is we have box k. Yeah, maybe we don't. Right, what we need is for k to be bigger than that. Yeah, so we just want this. Yeah, I should take back that statement. We need k to satisfy. We need the function k to satisfy being bigger than that. And if epsilon is like exponential, then k doesn't work. Doesn't like satisfy this inequality and doesn't let you apply the theorem. But epsilon is probably somewhere between linear and cubic, depending on realistic proof system. So we have box k, p of k implies p of k, because a proof of length k of cooperation leads to cooperation. And then because k is not a crazy big function, we get p of k. Boom. So that's Fehrbach cooperating with itself. Oh, and I should probably put for all k's here. And this is for all k greater than the threshold. So now you can ask questions. So like, be unsatisfied with this result now. So like, try and be like, but what if this? And is it like really that? And like, what if? Yeah. Let's move into like dissatisfaction mode.
I'm curious whether Jim feels that his answer about a question about the like symmetry of this was adequately answered by now.
I think I'm convinced.
Yeah, you said something about there being symmetry between C and D, but there is an asymmetry here, which is that if you find a proof of defection, you ignore it and keep searching. Mm-hmm. Hypothetically. Yeah. Even though you won't find one, we think. Right.
It's what you counterfactually would have done that matters.
Yeah. Yeah. Turns out you had to be the kind of algorithm that wouldn't have defected had you found a proof of defection.
Would the version of the algorithm that stopped if it found a proof of defection defect if that proof was...
Man, if it was searching in parallel for cooperation and defection, I think it would just depend very heavily on the search order.
Yeah, I think then you'd get...
Yeah, that sounds right.
Like you would get one or the other, because it'd be a program. But which one you got would depend, subtly on the proof search order. I think. I don't know. Yeah, other random musings.
It fails to exploit, can.
Oh, it doesn't exploit the cooperate bot? Yeah, so that's why Patrick and others developed this prudent bot thing that first kind of checks and see if the opponent is stupid. And if the opponent is stupid, it'll defect and exploit the opponent. And then if it realizes, it's like, okay, that's not going to work, then it tries to go for a cooperate scenario. And then if that's going to work, not going to work, then it's like, screw it. Then it defects. Is that fair?
That's fair.
No, that's
Okay.
prudent.
That's fair. Wow. Wow. Yeah.
So like, I guess this is kind of a technical question, but like if I know my proof system, like is there a way to calculate what k-hat is? Or?
Yeah, I'm pretty sure it's like 1 million.
Oh, okay.
Yeah, I don't know. Somewhere between 1,000 and 1 billion.
Okay.
Pretty sure. Yeah, for like whatever proof system I would make up. Piano arithmetic with abbreviate, you know, with like good encoding for numbers and yeah.
I mean, the length of the proof just seems to be equal to the length of the proof of Lorentz theorem, right? I mean, if they have enough length to just prove the bounded Lorentz theorem,
yeah,
then like,
right.
And also write down k.
Yeah, you have to write down the number k.
Yeah.
You have to prove this and then say, all right, now let k equals the number k.
The length of the proof of your theorem is number k.
Yeah. It's so weird, so loopy. Hofstadter is probably looping in his grave.
He's still alive. We can show him this.
Yeah. Whoa, really?
Yeah.
Oh man, I didn't know that. All right, good job, Hofstadter. Not going on the internet. Soon. Oh, you look like you had a thing. Okay, so another amusing consequence of this is that if you defined benefit of the doubtbot, which is the same benefit of doubtbot, is the same as fairbot, which tries to prove that you're going to defect. And if it finds a proof of defection, it gets angry at you and defects. But if it finds no proof of defection, it assumes you're innocent until proven guilty, right? And gives you cooperate. Seems like a nicer bot, right?
Yep.
But actually, benefit of the doubt bot defects against benefit of the doubt bot by Loeb's theorem.
The fun thing is when you do benefit of the doubt bot against fairbot.
Yeah. Okay. Wait. Let me remember this. Benefit of the doubt bot versus fairbot. At least in the. So I haven't thought about the bounded version, but in the modal version, benefit of the doubt bot finds fairbot finds no proof.
Shouldn't it be undefined for symmetry considerations?
No, it's got to be it's got to be a thing.
Always a fixed point.
Neither of them find no proof.
And then they both find no proof.
Fairbot defects. Benefit of the doubt bot cooperates. So fairbot exploits benefit of the doubt bot.
What a jerk. Yeah. All right. Yeah. Okay. So that's interesting. Counterintuitive stuff happens because Loeb's theorem is weird, because Gödel's theorem is weird. So you might also think, all right, what happens if you pit fairbot k against fairbot k plus 1? You know, the whole point of this exploration was like robust cooperation, right? So we didn't want ismebot is erased, right? But we're like annoyed that ismebot has to be exactly equal to its opponent, right? So it would be annoying if fairbot had to be exactly equal, like the k has to be equal, or it has to be, right? Like there's something dissatisfying about these things having to be basically the same agent, right? So after I proved this, Patrick yelled at me and said, "That's not good enough." He didn't really yell, but he told me it wasn't good enough. He said, Go back into your room and prove something better." And I was like, fine.
This is not accurate reporting.
What? It's not going on the internet. Yeah. So here's another result. We're going to define, and the definition is going to clue you into the result. There will be no surprise. So we got some agent like fairbot that has a parameter k in it, and we're going to say a sub k is g fair, where g is some function. So g n to n is some computable function, and g stands for generosity. So when your opponent is very complicated, you're going to be generous in your proof search. You're going to search longer to account for the fact that your opponent is complicated. So that's what g fair is. G fair, AK is g fair if a proof of length k plus the generosity function of the length of the opponent, length of opponent source code, of, oops, that shouldn't be P, that should be opponent cooperates with me. That opponent of a sub k equals cooperate. If this proof is sufficient to ensure that a sub k cooperates. Is that cool? So You're G-fair if you give a certain amount of generosity in your search for a proof of cooperation. And then notice I'm not writing if and only if here. So I'm not saying that that has to be your sole criterion. You could have other criteria for cooperation. You could also be like, also if my opponent has a comment that is a binary encoding of a cat video, then I will watch the cat video and then cooperate. So it doesn't have to be if and only if. It's explicitly, you can as long as your opponent being pretty good and simple, understandable to you, is enough for you to cooperate, then you're G-fair. Cool? So the theorem, and this is what I would just call robust cooperation of bounded agents, is that if A and B, so say, I think you want G, I think G you want it to be bigger than L cubed or something. So I think if G of L is greater than, I think it's like a similar function over 2 to the, I don't know what it is. Yeah, I think it's like L cubed. Then if A sub k and B sub k are both G-fair, then for all M and N greater than some threshold k hat, they cooperate with each other. Oh, that shouldn't be a k. That was the whole point of this. They don't have to be k's. And in particular, B could be like vastly more any than A is any. So it's like there's this intuition from, there's like some early results on finite automata cooperating with each other in game theory, where the reason they cooperate is that they can't think far enough ahead to defect or something. They can't, like, there are these games where, like, if you're the iterated prisoner's dilemma, like, you always defect in the last round, and, like, if you can't think far enough ahead, then you don't, and then you cooperate for a while, and then when you start getting close to the end of the game, you're like, screw it. So there's this, like, lingering intuition around where, like, cooperation is a symptom of boundedness. Like, there's this kind of mantra going around. At least a few economists that I've told this result to were like, well, of course they cooperate. They're bounded. That's what bounded things do. Check out these finite automata that cooperate because they're too dumb to defect. Yeah. And I'm like, that's not,
That's the opposite of what other people will yell at.
Yeah, the other people, right, exactly. So you just have to prove things. So anyway, so they cooperate with each other. So that's the robustness result. And I think I'll just like end there as like the punchline. Cool. Thanks.
Questions?
Oh man, I was aiming for 50. All right.
So how do we think that this might end up looking for things that do more heuristic search rather than brute force search? Because this is clearly like not something that you would efficiently compute.
Yeah, so the first thing I thought of the other day, which is, what, do I have Fairbot up here anymore?
Yeah, it's right there.
Oh, right here, yeah. So the first thing I thought about the other day is like, if you had some heuristic for assigning probabilities to mathematical statements, then instead of searching for a proof, you can instead do like, think about it for k time steps. Think for k time steps. And if you say like q sub k is your heuristic probability assignment to mathematical statements, you'd say like if q sub k of this statement is bigger than 90%, if you're like pretty sure that the opponent's going to cooperate, with an asterisk here, which says like, by the way, proving it makes you sure. Like proof of cooperation counts as being more than 90% sure. So, for example, by proving it.
Be coherent in some obvious ways like that. Yeah.
Yeah.
In some obvious ways like that.
Like in particular, if you find a proof of defection, it doesn't. like if you find a proof of cooperation and defection, you're still more than 90% sure. So it's a little symmetry breaking there.
Oh, I see.
Yeah, Scott pointed this out when I first thought about this. But anyway, so you have to have this like asymmetry, this counterfactual asymmetry. You have to have the property that if counterfactually you found both a proof of cooperation and a proof of defection, you would believe in cooperation instead. So you have to be like counterfactually self-fulfilling believer of goodness.
You have to be nice if the world is inconsistent.
Right. Or you have to be optimistic if the world is inconsistent. Yeah. And so anyway, then this thing is G-fair. So here we have a probabilistic reasoning thingy that does robust cooperation. So we're done. But all we need is this. Also, it's not clear whether the probabilistic, and you need the asterisk.
That's the only thing we need.
Yeah, that's right. Oh, you really, yeah, right.
Erase the rest, keep the asterisk.
Yeah, that's true. Keep the asterisk. Yeah, all you really need is the asterisk. It's true for the proof. But like, I'm just doing this to point out the obvious fact that if you have a probabilistic reasoner who also believes in proofs, like, then it'll work. Now, it's possible that it would, like, there's a question of whether this thing gets a lower k hat. So my proof goes through lobe and like gets a lower k hat. Maybe it doesn't. There's another thing you could do, which is like find the. So this is who thought of NicerBot?
I think that was Jessica's name.
Jessica.
If Stuart agrees it's Jessica, then it's Jessica.
Stuart, did you or Jessica invent NicerBot?
I don't remember at all, but people have told me I've invented things I don't remember.
All right, Stuart, it's Stuart.
I think that I invented it independently, but the name...
Sure, yeah, you're right. It's a fairly natural thing. So you could say, another thing you could do is basically cooperate, I'm not going to write it, cooperate with a slightly higher probability of cooperation than your opponent.
Yeah, you take the probability that they cooperate with you, and you cooperate with probability that plus epsilon.
Yeah. And so then the only fixed point, if this thing plays against itself, the only fixed point of that is they both cooperate. Yeah. That old thing. Yeah. So that's the thing you could do. That doesn't use Loeb's theorem to cooperate, but it is maybe another kind of like robust cooperation. And I think the whole point, I don't know, the whole thing that's exciting about all this is that like game theory has really not explored this like open source setup for stuff. So, and like AIs can be open source to each other. To an extent, we might be open source to AI. Like if it studies us enough, maybe it thinks it really gets us. Maybe AI is open source to us. It's like active area of research, make AI understandable, right?
Why do you think AI will be open source to each other?
They could be. I mean, I'm just saying in principle.
They could share code. Like if they decide that's a good way.
I could just email you and be like, send me your source code.
How can they prove that they are?
Yeah, exactly.
One proposal that's been mentioned is if you want to demonstrate your source code, you produce a source code file and say, all right, I am now going to, like, with your observation, make a new agent who this is their source code, and then when they're finished, I'm going to transfer all my resources to that agent. Now you know that this agent has this source code. Anyway.
And you have to prove that you're going to transfer your resources to them, which you probably do using banks.
There has to be some trusted hardware.
Yeah.
Well, no, like you build it with their observation. You transfer your resources, and then they can trust that thing.
Oh, nice. Oh, you just give it to them. You just like, here's all my stuff.
Yeah.
To that thing.
Yeah. Like this really is my source code, so I'm not losing anything by switching bodies.
Nice. Cool. Yeah. So yeah, there's like lots of computer security work that would go into like implementing the game theory of open source personal dilemmas, just like open source game theory in general. But it's just wide open, and like also the one-shotness is important, right? Because for existential risk, right? Like if the first round of the prisoner's dilemma is where like the thing can destroy you, or you can destroy it by not turning it on or by turning it off, or etc., right? You're not in an iterated game. You just want it to go well the first time. So I think the open sourceness and the one-shotness are like important things that game theorists need to be thinking about. And I'm not going to be pursuing this line of research much anymore, because I think It's to a point now where like I can give a random talk about it. Once I get it into some journal, I can give a talk about it at a game theory conference, and then maybe more people will think about it. I think there's like other stuff that I think is more important for value alignment than this. That's like still needs to get to a point where other people could be interested in it enough to do it. Yeah. Patrick is gesturing like, oh.
What does not P-blobe look like?
Oh, regular blobe? Yeah. What blobe could look like? Ask Stuart. I think Stuart, well, he's not going to do it either. Neither of us is going to prove it. Like, I think there might be some theorem of the so Stuart wrote a blog post outlining.
P-blobe looks pretty satisfactory to me, so I'm like not sure what you're holding out for.
Oh yeah, I mean, so I don't know. It'd be cool if you could prove something that doesn't have a for all quantifier in it. It just says if you have a proof of length n, that a proof of length k of p implies p. If n is sufficiently small relative to k, then you get p in some other function of n, something like that. And I think you could use this to prove that, because what happens is whenever you have a proof of a for all, that bounds the length of the proof for specific instances later. So you could use this, I think, to prove that. But whatevs. We already have robust cooperation. Yep. Cool.
All right. So let's thank Critch again.